Hello, I am Dr. Sigar Kanti, Associate Professor of Mathematics, Government First Year College, KR from Bangalore. In this video, I will try to prove some simple results in graph theory. Question number 1, define a walk and a path in a graph G. Okay, in a graph, say G, and then prove that there is a UV walk if and only if there is a UV path in G. Okay. First we define walk and path. Definition. Walk definition. It is nothing but the alternating sequence of the points and the lines, starting with a point, ending with a point, and every edge in that sequence is incident with immediately preceded and followed by the vertices. Okay, followed by it. Incident with the vertices, immediately preceded and followed by it. And we are not going to write the edges here, just we write the vertices. Okay, so in a sequence we write the vertices. So that is here. We write like this, define like this, an alternating sequence of points and lines or edges starting with a point and ending with a point starting with a point and ending with a point. It is an alternating sequence of points and lines. That is what I say, and the edges. Starting with a point and ending with a point. That's point, line, finally a point. And here one more condition is every edge in the sequence is incident with the vertices or points immediately preceded and followed by it. Okay, so that is like this, U1 and then say E1, U2, E2, U3, E3, U4. Okay, so this is a sequence of points and lines. Point, line, point, line, point, line, point. Alternating sequence of points and lines starting with a point here U1 and ending with a point U4. And here this is the edge E1 is an edge incident with the vertices immediately preceded and followed by it. That means here E1 is incident with U1 and U2 and E2 is incident with U2 and U3. E3 is incident with U3 and U4. So this is a walk. And what is a path? Path is nothing but it is a walk where the vertices are not repeated. Here in a walk, there may be repetitions of the vertices and repetitions of the edges. In a path, vertices are not repeated. Vertices are not repeated means consequently edges are also not repeated. So the definition of a path is, we go to the next page. Path, that is a walk, a UV walk, I will write, a UV walk where the vertices, are not repeated is called a path. A UV path is called a UV path. A UV walk where the vertices are not repeated and consequently edges are also not repeated is called a UV path. So that means here every path is a walk, but every walk need not be a path because vertices may be repeated in walk. Okay, so therefore every walk need not be a path, but every path must be a walk. Okay, I will go to the second part of this question. There is a UV walk. There is a UV walk if and only if there is a UV path. Okay, so here let me consider to prove the result. Let W1 be a UV walk. A UV walk. I will show that this W1 is a UV path. Now here, if vertices are not repeated in W1, then W1 is a UV path. Okay, if the vertices are not repeated, then W1 is a UV path. This is the required path. Now, if vertices are repeated, are repeated. So here, let me write W1 as a U1, U2, UI plus 1 and say again I am getting UI here, okay, UI and say UJ plus 1 or something, some vertex here, right, UJ plus 1 and so on, okay, where UI is equal to UJ, okay, UI is equal to UJ. UI is repeated. It is like this here. So this is our U1, U2, U3 and here this is our UI and here some vertices, some edges are here. Again this is nothing but UJ and then UJ plus 1 and so on. Okay. So what I do here is I will form a new walk consisting of lesser vertices here. What I do here is I will delete this part. Okay, I will delete this part. That is the all the edges after UI up to UJ, and I will delete UJ also. So that is I will consider UI only one time. Then the new path, new walk is, so that is here delete. Delete all the edges and vertices between UI and UJ. UI and UJ. Okay. Then resulting path is resulting walk is W2, U1, U2, UI, okay, UI is same as UJ, and then I will write UJ plus 1, okay, UJ plus 1, UJ plus 2 and so on. So is a path, is a walk consisting of less number of or fewer number of vertices than W1. So this is the new walk. new arc by deleting some vertices and some edges. Now again, if W2 has no repeated vertices, then W2 is a path. Okay, this is a path. And if W2 has repeated vertices, then continue the above process of deleting the vertices and edges between the same vertices. Okay, so that is here, if W2 has repeated vertices, then continue the above process, till we get the required path. Okay, so therefore here every UV walk contains a UV path, and conversely let P be a UV path. Then this implies P is a UV walk. Okay, that is here, every path is a walk, and if there is a UV walk, so we can find a UV path in that walk. Okay, so this is the result number 1. Next I will go to another result. One more result. Define a graph. Does there exist a simple graph? Does there exist a simple graph on 12 vertices and 28 edges, 12 vertices and 28 edges, such that degree of each vertex is either 3 or 4. Okay, the question is, does there exist a graph with 12 vertices and 28 edges such that degree of each vertex equal to 3 or it is equal to 4? And the first part is define a graph. We can define it is a graph is a non-empty set V called the vertex set, and together with the set E called the edge set, and every member of E set to join two members of E. That is the definition we have to write. So the second part. So here let G be a graph with 12 vertices and 28 edges such that degree of each vertex of G is either 3 or 4. Okay. Now here let me consider, let M vertices have degree 3 and N vertices have degree 4. Okay, so M vertices are of degree 3, N vertices are of degree 4. Clearly M plus N is equal to 12. Okay, the total number of vertices, and sum of the degrees is equal to twice the number of edges. We have this result. What is the sum of the degrees here? M vertices are of degree 3, n vertices are of degree 4. So therefore sum of the degrees is 3 into m plus 4 into n. So that is here 3 into m plus 4 into n is equal to 2 into number of edges here we have 28. Okay. So that is 3m plus 4n. That is here 3m plus 4n is equal to 28 into 2 is 56. So I will take this as a 2. Now here 1 implies, what is 1 here? 1 is m plus n equal to 12. Therefore m equal to 12 minus n. Using 1 in 2. N equal to 12 minus m. So that is here 3m plus 4 into n is 12 minus m is equal to 56. Okay. 1 implies. So using, we can write using 1 in 2. Okay. Now if I solve this equation, what we get here is 3m plus 4 into 12 48 minus 4m is equal to 56. So that is 3m minus 4m is minus m equal to 56 minus 48. This is equal to I think 8. Okay, 8. So that is here, this implies m equal to minus 8 is a contradiction. Is a contradiction because m is the number of vertices. Number of vertices is either 0 or it is greater than 0. I am getting a negative quantity here, m equal to minus 8. So this is not possible. They are getting a contradiction here. Therefore, such a graph does not exist. Such a graph does not exist. Right? Next, I will go to one more example, one more result. Next result, prove that a simple graph prove that a simple graph with minimum degree 2 has a cycle. Okay, prove that a simple graph with minimum degree 2 has a cycle. So what I do here is, I will consider, let G be a simple graph, G be a simple graph with minimum degree delta G greater than or equal to 2. I had to show that this has a cycle. Without loss of generality, let me consider G is connected graph, or otherwise consider the connected component of G. Okay, so here without loss of generality, let G be connected. Okay, or otherwise we can consider the connected component of G. Now here I have considered that G is connected. Let G has P vertices. Okay, G has P vertices. I have to show that G has a cycle. If G has no cycles, then G is a tree. Now here, if possible, G has no cycles. I have taken G is a connected graph. And if this G has no cycles, then G is a tree. Okay. Then G is a tree. If G is a tree, then number of edges is equal to P minus 1. We have this result in tree. Okay. Now here in this graph G, sum of the degrees is equal to twice the number of edges. Okay. Twice the number of edges. Or we write 2 into Q is equal to sum of the degrees. Sum of degrees. But here G has P vertices and degree of each vertex is at least 2. Therefore, sum of the degrees is greater than or equal to 2 into P. So that is, this implies Q is greater than or equal to P, or we write Q is greater than P minus 1. So if I take this as 1 and this as 2, so here this is a contradiction. This is a contradiction because here we have, according to our assumption, Q must be equal to P minus 1. What I am getting here is Q is greater than P minus 1. This is a contradiction. Why we are getting this contradiction? We have taken if possible G has no cycles is wrong. So therefore here G has a cycle. Okay. G has a cycle. Okay, thank you. I will stop here.